And on August 30th, 2026, if the current launch schedule holds, a Falcon Heavy rocket will lift a new telescope away from Earth. Its mission is not simply to photograph distant stars. It has been built to investigate the invisible structure of reality itself. This is the Nancy Grace Roman Space Telescope, and if it works as planned, it may force us to rewrite the story of the universe. Roman does not look like a machine that should transform cosmology. Its primary mirror is 2.4 meters wide, the same basic size as Hubble's. Hubble has been orbiting Earth since 1990, sending back some of the most important images in the history of science. So at first, Roman may sound like another Hubble. It is not. Hubble sees the universe through something like a narrow window. Roman will open the wall. Its wide-field instrument has a 300-megapixel camera and a field of view roughly 200 times larger than Hubble's main infrared camera, while maintaining comparable sharpness. In a single observation, Roman can capture an enormous population of stars and galaxies that Hubble would need a mosaic of hundreds of separate images to cover. The difference is not merely about taking larger pictures. It is about statistics. A rare object may never appear inside a narrow field. A rare event may begin and end while no telescope is looking. But when a telescope can repeatedly observe huge regions of the sky with extraordinary precision, the rare becomes measurable. Roman is expected to survey the sky at speeds far beyond Hubble's. During its first 5 years, it could capture more than 50 times as much sky as Hubble has observed in more than 3 decades. Its archives may eventually contain measurements of light from 1 billion galaxies, hundreds of millions of stars, and more worlds than every previous generation of planet hunters combined. But before Roman can see any of them, it has to survive the morning of August 30. The current plan calls for liftoff at 11:26 UTC from Launch Complex 39A at NASA's Kennedy Space Center in Florida. The rocket beneath it will be a SpaceX Falcon Heavy. Inside the protective fairing will be an observatory assembled from millions of individual parts, tested with violent vibration, deafening sound, and the temperature extremes it will face beyond Earth. Roman has already been filled with approximately 290 gallons of hydrazine fuel. That fuel will not carry it all the way through space like a conventional journey. After the rocket provides the initial energy, Roman will use its own propulsion system for corrections, orientation, and the delicate work of maintaining its future orbit. Its destination is not low Earth orbit. Roman is going approximately 1.5 million kilometers from Earth to the region around the second Sun-Earth Lagrange point, known as L2. L2 is not a platform, and it is not an object. It is a region where the combined motion and gravity of the Sun and Earth allow a spacecraft to remain in a relatively stable relationship with both. Roman will move in a large orbit around this invisible gravitational balance point, sharing the general neighborhood used by the James Webb Space Telescope. From there, the Sun, Earth, and Moon will remain on roughly the same side of the spacecraft. Roman can shield itself from their heat and light, keep its instruments cold and stable, and look outward into deep space. The telescope will not become operational immediately. About 5 hours after launch, its solar panels and sunshade are scheduled to deploy. Around 2 days after launch, its high-gain antenna will deploy, and the cover protecting its aperture will be released. The Coronagraph instrument is expected to activate after roughly 1 week. The wide-field instrument will begin its initial checkout after about 3 weeks. Then comes alignment, focusing, calibration, and testing. For approximately 3 months, engineers will turn a launched machine into a functioning observatory. If everything proceeds as planned, Roman's first public observations will arrive near the end of that commissioning period, and then the real investigation begins. The universe is expanding. We have known that for about a century. Distant galaxies are generally moving away from us, not because Earth occupies the center of an explosion, but because space itself is stretching. Wherever an observer stands, sufficiently distant galaxies appear to recede as the distance between large cosmic structures grows. For decades, scientists assumed gravity should gradually slow this expansion. Everything with mass attracts everything else. Even if the universe continued expanding forever, the expansion should lose speed. But in the late 1990s, astronomers studying distant exploding stars found the opposite. The expansion of the universe was accelerating. Something appeared to be working against gravity on the largest scales. Something woven into empty space seemed to be driving galaxies apart. That unknown influence became known as dark energy. According to the standard cosmological model, dark energy makes up roughly 2/3 of the total contents of the universe. Yet no one knows what it actually is. It might be a constant property of empty space. In Einstein's equations, a cosmological constant can produce an effect resembling the acceleration we observe. If this is correct, dark energy does not need to be a substance moving through space. It could be an energy inherent to space itself. As the universe expands and creates more space, the total influence of this energy becomes increasingly important. But that may not be the full story. Recent measurements have kept alive the possibility that dark energy could change over cosmic time. The evidence is not yet conclusive. But if dark energy evolves, then the simplest version of our standard model may be incomplete, and the consequences would extend far beyond a correction in a physics textbook. The nature of dark energy may determine the final fate of everything. If it remains constant, the universe may continue expanding until distant galaxies disappear beyond our observable horizon, stars burn out, and the cosmos approaches a state of darkness and near maximum disorder. If dark energy weakens or changes sign, other futures may become possible. Under some models, expansion could eventually reverse. Under more extreme models, a growing form of dark energy could someday overpower galaxies, solar systems, planets, and even atoms in a big rip. Roman will not wait until the end of time to discover which possibility is correct. It will look backward. Because light takes time to travel, distant galaxies appear as they were billions of years ago. By measuring enormous numbers of galaxies at different distances, Roman can reconstruct how cosmic expansion changed across history. It will approach this problem in several independent ways. One method uses exploding stars called Type Ia supernovae. These explosions occur in systems involving white dwarfs and can serve as standardized distance indicators. If astronomers determine how bright such an explosion should be and compare that with how faint it appears, they can estimate its distance. By observing many supernovae across different periods of cosmic history, Roman can trace how quickly the universe was expanding when their light began its journey. But supernovae alone are not enough. Every method can hide systematic errors, so Roman will also examine the distribution of galaxies themselves. The early universe was filled with hot matter and radiation through which pressure waves traveled. Those ancient waves left a preferred scale in the way matter later gathered into galaxies. The imprint is called baryon acoustic oscillation. It acts like a ruler written across the cosmos. By measuring how the apparent size of that ruler changes with distance, scientists can test the history of expansion. Roman will also study weak gravitational lensing, one of the strangest consequences of Einstein's theory of gravity. Mass bends space-time. When light from a distant galaxy passes near intervening matter, its path bends. A massive galaxy cluster can produce obvious arcs and multiple images, but most lensing is far more subtle. The shapes of background galaxies become distorted by amounts too small to recognize in a single object. Across hundreds of millions of galaxies, however, the pattern emerges. Most of the lensing matter will not be visible. Roman will effectively use distorted galaxies to map dark matter, the hidden framework around which ordinary matter has gathered. It will reveal where invisible mass lies, how it clumps, and how its structure grew while the universe expanded. That comparison is crucial. Gravity pulls matter together. Dark energy drives large-scale expansion. The history of cosmic structure records the struggle between them. If the map produced by Roman does not match the predictions of general relativity, the mystery may be deeper than dark energy. The acceleration could be telling us that our theory of gravity changes across enormous distances. A theory that works beautifully around planets, stars, and black holes may not be the final description of the universe as a whole. Roman is therefore not just searching for an unknown ingredient. It is testing the rules themselves. And while it maps billions of galaxies, another investigation will be unfolding much closer to home, inside the crowded center of the Milky Way. Most planets discovered so far were found because they crossed in front of their stars or pulled on them gravitationally. These techniques are powerful, but they favor particular kinds of planetary systems. A planet close to its star is more likely to transit. A massive planet creates a stronger gravitational signal. The result is a census filled with worlds that are easiest to detect, not necessarily worlds that are most common. Roman will search for planets through a different effect, gravitational microlensing. When a foreground star passes almost perfectly in front of a more distant star, the foreground star's gravity bends and magnifies the background light. The distant star temporarily appears brighter. If a planet orbits the foreground star, its own gravity can add a smaller disturbance to that brightening pattern. The two stars may be separated by thousands of light years. They have no physical connection. Their alignment is a brief accident visible only from our moving position in the galaxy. It may never happen again. Some planetary signals last only hours. That is why Roman's combination of a wide view, sharp vision, stability, and repeated observations is so important. The telescope can monitor vast numbers of stars toward the galactic center and wait for space-time itself to reveal otherwise invisible worlds. Microlensing can find planets far from their stars, including analogs of the colder worlds in our own solar system. It may detect planets smaller than Mars. It may reveal systems thousands of light years away and help determine whether the architecture of our solar system is common or an exception. Roman's observations are expected to uncover thousands of planets through microlensing, while the same data may reveal as many as 100,000 additional planets passing in front of their stars. But the most haunting discoveries may be worlds with no stars at all. Planets can be thrown out of their systems during gravitational encounters. A young planetary system is not always calm. Massive worlds migrate, orbits destabilize, and close encounters can eject a planet into interstellar space. From that moment on, the planet circles the galaxy alone. No sunrise ever returns. No familiar star marks the passage of a year. Any surface ocean would freeze beneath layers of ice, although internal heat might survive below. These rogue planets produce almost no visible light, making them extraordinarily difficult to find. But they still have mass, and mass still bends light. Roman may be sensitive to rogue worlds with masses comparable to Earth and possibly below. If it finds them in large numbers, the number of planets in the galaxy could exceed the number of stars by far more than we currently know. The Milky Way might contain an enormous hidden population of worlds drifting through the dark between solar systems. Roman will not only infer planets through changes in distant light, its second instrument is designed to help take the next step toward seeing some of them directly. A star can be billions of times brighter than the planet beside it. Trying to photograph that planet is like searching for a firefly beside a lighthouse from thousands of kilometers away. The problem is not merely magnification. The star's light spreads through the optical system and buries the faint planetary signal. Roman's Coronagraph instrument will use carefully shaped masks, deformable mirrors, sensitive detectors, and extreme control of incoming light to suppress the glare of selected stars. It is a technology demonstration rather than Roman's primary survey instrument, but its importance may reach far beyond this mission. The coronagraph could directly image large planets around nearby stars and study disks of material from which planetary systems form. More importantly, it will test technologies needed for future observatories that may photograph small, rocky planets resembling Earth. Roman is unlikely to take a detailed portrait of another Earth, but it may prove that the path toward such a portrait is possible. That future image would still be only a point of light, yet hidden inside that point could be the chemical fingerprints of an atmosphere, clouds, surface conditions, and perhaps signs that cannot easily be explained without biology. In that sense, Roman is a bridge. Hubble showed us the deep universe in exquisite detail. Webb is examining some of the earliest galaxies and probing the atmospheres of selected distant worlds. Roman will add scale. It will find the populations, patterns, anomalies, and rare targets that narrower observatories can later examine closely. Webb can study individual trees. Roman will reveal the forest. And in a forest containing billions of galaxies, it will inevitably find things it was not specifically designed to find. It may catch stars being torn apart by black holes. It may discover supernovae in their earliest moments. It may expose previously unknown dwarf galaxies dominated by dark matter, find quasars from the young universe, track objects moving through our solar system, and identify cosmic explosions that appear without warning and fade before most telescopes can respond. The greatest discovery may not appear anywhere in the mission plan. That has happened before. Hubble helped reveal that cosmic expansion is accelerating, a discovery central to the reason Roman now exists. Scientific instruments often become most powerful when nature presents something their designers did not predict. Roman's real product will not simply be images. It will be an immense, changing record of the infrared sky. The data volume will be so large that much of the science will depend on automated processing, cloud-based analysis, and astronomers searching the same observations for entirely different phenomena. One team may use a field to measure dark matter, another may search it for distant supernovae, another may identify planets. Years later, someone may return to the archive with a question that has not yet been imagined. This is why Roman's wide view matters. A beautiful image can change how humanity sees the universe. A sufficiently large survey can change what humanity believes the universe is. The telescope carries the name of Nancy Grace Roman, NASA's first chief astronomer. Decades before Hubble reached orbit, she helped build institutional support for a powerful space telescope at a time when the idea was uncertain, expensive, and difficult to realize. She later became known as the mother of Hubble. Now a telescope bearing her name will take Hubble's level of sharpness and apply it across areas of sky that Hubble could never efficiently survey. Roman's primary mission is planned to last 5 years, with enough onboard fuel potentially supporting another 5. That lifetime may sound short compared with Hubble's decades in orbit, but Roman has been designed to collect an extraordinary amount of information quickly. The challenge may not be whether it sees enough. The challenge may be whether we can understand everything it sees. And none of these discoveries are guaranteed. The launch date can change, rockets can be delayed, deployments can fail. Instruments can behave differently in space than they did on Earth. Dark energy may refuse to fit any dramatic new theory. The data may strengthen the cosmological constant rather than overturn it. Roman may give us better measurements without giving us a satisfying explanation. That possibility is not failure. Knowing that dark energy behaves exactly like a constant would eliminate many alternatives and narrow the search. Discovering that general relativity survives its largest test would tell us something profound about the durability of Einstein's theory. Finding that our solar system is common or extremely unusual would change how we understand our own existence. Science does not promise the answer we want. It constructs a way for reality to answer. On August 30, the Roman Space Telescope is scheduled to rise above Florida inside a column of fire. For the first few minutes, its future will depend on engines, guidance systems, separation mechanisms, and thousands of decisions made years before the countdown begins. Then the rocket will release it. Roman will travel outward, deploy its power systems, uncover its mirror, and begin the long process of focusing on a universe that is mostly invisible. 3 months later, if everything works, the first images will arrive. They may look like wide fields of stars and galaxies, but behind those points of light will be a much larger investigation. Roman will watch gravity bend the images of distant galaxies and turn those distortions into maps of matter no human eye can see. It will measure ancient explosions to reconstruct the expansion of space. It will search for the fossil imprint of sound waves from the early universe. It will use momentary alignments of stars to discover planets hidden across the Milky Way. It may find frozen worlds wandering without suns. And it will test the technology that could one day allow us to see another planet like our own. All of this will be done because the visible universe is only the surface. Beneath every galaxy lies an invisible structure. Between the galaxies, an unknown influence is changing the scale of space itself. Together, dark matter and dark energy shape almost everything we observe, while remaining almost completely unknown. We have given names to the darkness. Roman will ask whether those names describe reality, or merely hide how little we understand. The telescope may confirm the universe we think we know. It may reveal that dark energy changes with time. It may show that gravity behaves differently across cosmic distances. Or it may find something no current theory has prepared us for. In a universe where 95% of reality is hidden, surprise is not the unlikely outcome, it is the one we should expect.